All right, this is video 2, section 11.6, and we're going to practice performing row operations on a matrix. All right, so here's a matrix. Let's practice giving the row operations. So let's interchange row 1 and row 3. So row 2 stays the same, row 3 becomes row 1 and vice versa. So 1, -3, 3, 4, 2, -1, 2, 6, 1, 2, -1, 3. All right, we're going to go back to the original matrix for each of these row operations. We're going to multiply row 2 by 2. So 1, 2, -1, 3, 4, -2, 4, 12, 1, -3, 3, 4. And finally, we're going to multiply row 3 by 4 and add it to row 1, replacing row 1. All right, so let's go ahead and multiply row 3 by 4. Well, the way I like to do this is I just like to write it below on the original matrix. So multiply row 3 by 4. So that's 4, -12, 12, 16. And I'm going to add that to row 1 to get a new row 1. So 4 plus 1 is 5. -12 plus 2, -10. 12 minus 1, 11. 16 plus 3 is 19. And now rows 2 and 3 are just the same. That's just a little practice performing our row operations on a particular matrix. All right, again, what were our goals for the row operations? Well, one of our goals that we talked about was getting our matrix into row echelon form, okay? So this means there's ones on the diagonal. Here's where my bar is. Sometimes we write it, sometimes we don't. There's where my bar is. Ones down the diagonal and zeros below all those and the numbers in the other points. Remember we did an example in the first video where we can translate a matrix back from row echelon form to a system of equations, and then it's in triangular form and we can easily solve the system. Another thing we can kind of aim for, and this is what mostly we'll be using computers for, is putting in reduced row echelon form. This is even better. This means for your coefficient part of the matrix, you only have ones on the diagonals and zeros everywhere else. And this is even better because if we translated this back, and let's just put some numbers in here, like let's pretend this is a 3, this is a 2, and this is like a -1. If we translated this back to a system, it would tell us that z is -1, y is 2, and x is 3, whatever those numbers are, because there's only ones for the coefficient of each individual variable. So right off, it'll tell you the answer to your system of equations. All right, the best way to do this is to just do some examples. So let's go ahead and we're going to take this system of equations and we're going to put it into a matrix, and then we're going to put that matrix into row echelon form. This whole process of taking a system, putting it into a matrix, using row operations to get it to row echelon form is called Gaussian elimination, named after a mathematician, Gauss. I have a couple dots on here. All right, so the first thing we're going to do, the very first thing we're going to do is we're going to put the system of equations into put system of equations into an augmented matrix. And actually, I don't want this to be 6. I want this to be 7. I just wrote down the wrong problem. So just make that 7. So my system of equations is going to be 2x plus 3y equals 7. 1x minus 1y equals 1. And now I'm going to use row operations to get this matrix into row echelon form. Use row operations to put this into row echelon form. Row operations are a lot like what we did for elimination method. All right, so the first thing I need to do to get this into reduced echelon form, well, I need to get this to be a 1, right? I need to get that to be a 1. And the way I'm going to do that is I'm going to take 1/2 times row 1, and I'm going to add, and I'm going to replace row 1 with that. That will make that a 1. All right, so row 2 isn't changing. I'm going to recopy that down. Row 1 is equal to 1/2 of its previous value. So 1/2 of 2 is 1, 1/2 of 3 is 3/2, 1/2 of 7 is 7/2. All right, my next step that I'm going to do is I'm going to get rid of this 1, right? I want that to be a 0, to be in row echelon form. So to get that to be a 0, I'm going to multiply -1 times row 1, add that to row 2, because that would be -1 plus 1. That would give me 0, and I'm going to replace row 2 with that. All right? So this time, I'm not messing with row 1. It stays the same. I'm replacing row 2. So I'm taking -1 times row 1. I just like to write it above sometimes. So that's -1, -3/2, -7/2. And I'm adding that to row 2, and that's going to be my new row 2. So -1 plus 1 is 0. -3/2 minus 1 is -5/2. So -3/2 plus -1, that gives me the -5/2. -7/2 plus 1 is equal to -5/2. All right, so now my matrix is almost into row echelon form. I just need this -5/2 to be a 1. Well, what do I multiply -5/2 by to get to 1? Well, it's got to be negative, right? Because a negative times a negative will give me my positive 1, and it's got to be the reciprocal 2/5. -2/5 times row 2, and I'm going to replace row 2 with that. All right, so we'll come up here. And so row 1 is still the same, 1/3/2, 7/2. Row 2, I'm now multiplying each value by -2/5. Well, 0 times -2/5 is 0. -2/5 times -5/2 is 1. And again, -2/5 times -5/2 is 1. And now my matrix is in row echelon form, and I can retranslate it back to systems of equations to solve it. This line tells me that y equals 1, right? This line tells me that x plus 3/2 of y, which is 1, is equal to 7/2. Subtract 3/2 from each side, and I get x equals 4/2, which is 2, and so my solution is 2, 1. And that's how we solve a system of equations using a matrix. So let's recap what we did. We first put the system into an augmented matrix, then we used row operations to get it into reduced echelon form, and then we translated it back and solved for the variables, because row echelon form translates back to triangular form of a system of equations.